Today's lesson is on how to draw Lewis dot structures. So we've seen dot structures before in my class. We've drawn dot structures for individual atoms of an element where we would look at what their location is on the periodic table and represent how many valence electrons that atom would have with dots around the element symbol. We also were able to draw dot structures showing ionic compounds where we saw the result of the transfer of valence electrons from the cation to the anion and the resulting charge of those element dot structures. We're now going to draw Lewis dot structures for my covalent compounds where we're going to be showing those shared pairs of electrons between the atoms, which is where these lines and these dot structures come in. So for today's notes, we're going to have our notes page on Lewis dot structures. We are also going to, at the end of this lesson, do some practice examples from our Lewis dot structure. We're actually going to be chewing through this. Oh my gosh, there's so much practice in here. We're going to be chewing through this throughout the next course of the lessons. We'll eventually get into naming what molecular shape each one of these dot structure compounds are, and if the molecule is polar or nonpolar. So that'll be really fun for us to build onto. And since we're dealing with valence electrons that are being shared, it will be super helpful for you guys to have out your periodic table showing the number of valence electrons depending on what group you're in. I feel like we're getting a lot of mileage out of our periodic tables that we have labeled and colored, and that is a good thing. So we will be needing those sources, our resources for us today. So let's get into the quick little lecture before we start drawing some practice. Okay, so Lewis dot structures and the octet rule. A Lewis dot structure is a 2D visual diagram that shows the sharing of valence electrons in a covalent compound or a molecule. In molecules, we know that atoms achieve a stable octet or 8 valence electrons by sharing those electrons. And the bonds formed from this sharing can be a single bond, a double bond, or even a triple bond. We've talked about this in our previous lesson. We talked about how my single bonds are my longest bond type and my weakest. We talked about this in terms of the game Red Rover. It would not take a lot of effort for me to break through only one hand sharing situation. Versus my triple bond over here, it is the shortest and the strongest. 3 shared pairs of electrons is going to make that a very strong bond and very, very difficult for it to be broken. Main thing to keep in mind here is whenever I see a line between 2 atoms, one line represents 2 electrons that are shared equally between the atoms. So here with my single bond, that is a pair of electrons. Here with my double bond, that is 2 pairs of electrons, or 4 total. And here with my triple bond, that is 3 shared pairs of electrons, or 6 total. So here's some examples of Lewis dot structures and how that satisfies the octet rule. Bonds are formed with available valence electrons so that every atom in the molecule has 8. Let me give a few examples of what we're going to be talking about here. So let's zip in and look at this oxygen atom in my water molecule. If we know that each one of these lines has 2 electrons, yes, they are shared between both of the atoms, but that's like oxygen's feeling like, yeah, those 2 are kind of mine too. So he's feeling satisfied when he has a bond line connecting him. Those shared pair of electrons, oxygen is thinking that counts as 2 electrons for him in his valence shell. So if I were to look at oxygen and count his valence electrons, I would go 1, 2, 3, 4. Each dot represents 1 valence electron, right? And then in this line, there's 2 in there, so 5, 6. And in this line, there's 2 in there, 7, 8. He's got 8. He feels good. Now, if I zip on over here to this carbon in my carbon dioxide molecule, you're like, he don't got no dots around him. That is fine. Hopefully all 8 of his valence electrons that he got from this bonding process are in the shared bonds. Let's see. So each line represents 2 electrons shared. So we would have 1, 2, 3, 4, 5, 6, 7, 8. Yes, he is happy. He's got 8 valence electrons. And now also the rule here is with my dot structures and forming covalent compounds is everybody in this molecule has got to be happy with 8 valence electrons. So I can look at the oxygens over here too. Let's pick one of these guys out and count and see if he has 8 also. 1, 2, 3, 4 dots, 5, 6, and 7, 8. Yes, so it works. Let's quickly do this last one right here and look at this central atom of carbon and CH4. he's got 4 bond lines. And if each one of these bond lines is 2 electrons, he's got 8. I'm not going to spend every single example working through and explaining how each one of these have 8. We've got lots of examples where we will practice counting all of this stuff. So let's move on. Cool. When you draw a Lewis dot structure and it obeys the octet rule, it feels good, doesn't it? But there are some exceptions to the octet rule. You're like, oh my gosh, you gotta be kidding me. Yeah, not all atoms require 8 valence electrons in order to be stable. Some are happy with less than 8. You do need to know these 3 exceptions to the octet rule of atoms who are okay with something fewer than 8 valence electrons. The first example I feel like is maybe the most obvious, or the one that makes the most sense, is I've got hydrogen here. He's cool with if I were to bond 2 hydrogens together with only one bond line connecting them. A bond line is 2 electrons, so that means each one of these hydrogens has 2 valence electrons. But that's okay for a hydrogen, because remember, hydrogen's valence shell is just the first energy level. And we know the first energy level only can hold 2 electrons in that 1s sublevel. So that's a full shell for hydrogen. Okay, notice I put and helium here in parentheses, and you're like, whoa, now helium is a noble gas. Yes, he's a noble gas, and we know the noble gases are unreactive. Usually, every now and then you may see a noble gas do something weird and freaky and try to decide he wants to bond. So if helium would like to bond, which is not very common, since he is only one occupied energy level, would be okay with 2 valence electrons. Okay, boron. Boron is fine with only 6 valence electrons. That's what makes him happy. Look at him right here. I have boron trihydride, and he only has 3 lines connecting to other atoms. Well, each one of those 3 lines has 2 valence electrons, so he is okay with 6. And finally, my last exception to the octet rule, this may be a little bit freaky, I've got beryllium. You're like, whoa, now, beryllium is a metal. Yes, he is a metal, but sometimes, specifically because he's a very, very, very small metal, he kind of likes to share things because he's kind of electronegative in terms of metals, right? So he's fine with only 4 valence electrons when he's able to make a covalent bond. So when I see 2 lines coming off of beryllium, I'm like, not to be scared. That is fine for beryllium. He is cool with 4. Boron is cool with 3 and 6, and hydrogen is cool with 2. Those are my exceptions to the octet rule. We got some more exceptions. Some atoms are cool with more than 8 valence electrons. You're like, I absolutely give up. You do not need to know any of my expanded octets, but I thought it would be cool to show you them because they create some really, really interesting shapes that I'd love to show some examples of when we get into our lessons on VSEPR and molecular geometry. So looking at this guy right here, I've got phosphorus, pentafluoride, right? So he's got 5 bond lines coming off of him, and each one of those 5 has 2 valence. He's cool with 10. That is weird. Okay, and I got this one. This is wackadoo. Look at this, xenon tetrachloride. Another example of sometimes maybe a noble gas decides he wants to bond. We do not worry about that. He's got 4 bond lines, so 8 valence electrons in those bonds with the chlorines, but he's also got 9, 10, 11, 12. He's cool with 12 valence electrons. That is weird. And here's sulfur hexafluoride. He's got 6 bond lines. So once again, he's cool with 12. Very cool structures can come about here with these covalent bondings. You are not required to know the exceptions of the octet rule of atoms that are okay with more than 8. All right, so we got steps for drawing Lewis dot structures. There are some steps here. One does not simply draw the Lewis dot structure. There is some rules and organization that's required to get to that point. Okay, the first thing, and we have all of this on our notes page, and I think that these notes are, these steps are rules on how to draw Lewis dot structures are much better understood when we actually use them to go through our examples. So I am going to go through this PowerPoint slide pretty quickly, and then we will actually execute these rules and see how they apply when we do our example problems. But the first thing you are always going to do is you're going to count up the total number of valence electrons available. By total number, I mean all of the atoms in that molecule. You are going to look at them and you're going to see where they are on the periodic table, and where they are on the periodic table, you're going to be like, great, you have this many of valence electrons. But I'm going to do that for all of the atoms in the molecule. I'm going to add them up. So for this example, we know carbon is in group 14, so he's got 4. Hydrogen, he's in group 1. He's got 1 valence electron, right? And then chlorine is in group 17, so he's got 7. So here I am adding up all the total electrons. That 4 from the carbon, each one of those one valence electrons from the 3 hydrogens in my formula, and then the 7 from the 1 chlorine. So I have 14 total electrons, total valence electrons, that are going to be distributed in some way to all of these atoms in order for them to all be satisfied. Okay, I can also draw Lewis structures of my polyatomic ions. Okay, if you have a polyatomic ion with a positive charge, we know a positive charge comes from losing electrons. So when counting my total number of valence electrons for a positive polyatomic ion, I would just subtract the number of electrons that would be equal to the charge. That would represent how many electrons was lost before you have that polyatomic ion to complete the structure for. If I have a polyatomic ion with a negative charge, though, that means electrons have been gained. So I would just add those appropriate number of electrons to my total electron count when I'm doing this first step. Cool. All right, we are up next. Step number 2 is to place the central atom in the center of your page. And then I will place the remaining atoms on the outside. So notice I have not drawn any dots or lines. I have just drawn letters of the alphabet here. I have put the central atom, which is carbon, here in the middle. And then I put all of the other guys just, randomly kind of around him. Maybe in some way that makes somewhat sense to where if they do need to bond to that central atom, that they are not like way over here in outer space. We maybe want them kind of close to that central atom. But y'all may be asking, well, how did you know carbon was in the middle and not some of the other ones? There are some kind of guidelines on how to pick the central atom. Usually it will be quite obvious, okay? Usually it's written first in the formula. Usually it is the least not least common, the one that is in the fewest amount, because usually in all these Lewis dot structures we will have an atom that there is only one for. Specifically here for this carbon, he's got one of him, and he is most commonly going to go in the middle here. But I also had one chlorine. This is where this first little guideline is. It's the least electronegative atom in the formula. So we know electronegativity increases up here to this top corner, right? Okay, well, chlorine is way closer up to this corner than carbon is. And if you ever need to, you can check on the back of your yellow periodic table and look at those electronegativities and pick out which guy is going to be the least electronegative if you're having some difficulty trying to identify who's going to go in the middle. I also said it's the least abundant element in the formula. It's maybe listed first, and it needs the most valence electrons. What I mean by that is, you guys, hydrogen is never going to be in your central atom. Like, he can only make one bond. He only wants 2 valence electrons. So we're going to have to kind of keep those exceptions to the octet rule specifically with hydrogen in mind when we are drawing our Lewis dot structure. So what we have done here is we got my central atom in the center, and I just speckled around all my other letters of the alphabet for the other atoms around that central atom. Well, so remember my count. Remember my counter that we did on the first step. We said we had 14 available valence electrons from all of these atoms. So the third step says we're going to use 1 pair of electrons to bond each of those outer atoms to the central atom. The goal of this is we cannot have some of these guys flying away. I've told you these guys are in a molecule, so they better be all connected in some way. So I've got to bond them to the central atom. So what I have done here is every single bond line I have drawn is 2 electrons that I have got to remove from my electron counter here. So I have used up 1, 2, 3, 4, 5, 6, 7, 8 electrons from my original 14 valence. So I crossed off 14, I wrote -8, and now I have 6 more electrons left to put in here in some way or another. We're getting to that, okay? But the goal here is I got to bond everybody up to the central atom and then remove how many electrons that took for me to do that from my original total electron ticker. Ticker, I don't know if it's the correct way to say it. Whatever, count, whatever thing. Okay, so now step number 4 is whatever remaining electrons I have. So we had 6 after bonding everybody to the central atom. I am now going to distribute those remaining electrons to all of my outer atoms to give them a full valence shell. So I'm going to do that first. And after that, after everybody's full on the outside, I'm going to look at that central atom and distribute any remaining electrons to him to give him a full valence shell. if he needs it. So let's look here. On this side, I've got four different, or not four different, but I have four outer atoms here. The good thing is my hydrogens, they are already happy. Remember, they each one have a bond, so they each have 2 electrons, right? So they are stable and happy. My chlorine needed some taking care of. He only had a bond to carbon, which means he only had 2 electrons. So I needed to draw 1, 2, 3, 4, 5, 6 dots around him to represent lone pairs. If you've noticed, I've put 2 dots next to each other on each one of the remaining sides of chlorine. I think we've mentioned it before when we practiced drawing dot structures, is that we're going to need things in pairs. Yes, if I have any lone pairs of electrons in my Lewis dot structure, meaning any electrons that are not involved in a bond between 2 atoms, they will always come in pairs. But I needed to draw 6 of those around the chlorine because 6 plus this 2 in that bond with carbon will make him happy with a satisfied shell of 8. But after I've drawn those dots, I've got to go to my ticker here and accommodate for, well, how many more electrons have I used up by doing that? We put 6 electrons on him. Oh my gosh, we are no more valence electrons left. That's it. That is all I had. And I have not even read the second half of this rule. I needed to distribute the rest to the central atom. I've got carbon still to keep in mind. But check. Carbon. Y'all, he already has 8. So he's totally happy. So after you've done this, you're like, fill up all the outer atoms when they're happy. Make sure that central atom is happy, and then you are good to go. We love this. This is easy enough, right? But sometimes after this step, when I'm out of valence electrons, I go to the central atom and I'm like, oh no, you only have 6. Or, oh no, you only have 4. What do I do now? You guys, this is where we get to make double bonds and triple bonds. So if there are not enough electrons after step number 4 to give all my atoms a full valence, you get to make multiple bonds. Specifically, if you are 2 electrons short, meaning if that central atom only has 6 valence electrons and he's like, I need 2 more, but I cannot have any more. I got my ticker down to 0. You're actually going to take a pair of electrons from the least electronegative outer atom and use it to form another bond between it and the central atom. And this is probably going to be much more understood when we do some practice examples together. But what I have done here is after I've connected everybody up to nitrogen with 1 bond, and then I filled everybody up on the outside with their lone pairs, and then I zoomed in and tried to fill everybody on the central atom to make sure he's happy. What happened here is this nitrogen was only 6 electrons. So he had to look at his 2 buddies and be like, which one of you is least electronegative, right? Okay, well, the least electronegative atom is the one who wants their electrons the least, which means he will be more likely to be able to share. So what I ended up doing was taking a lone pair from the oxygen atom and said, okay, that pair of electrons now will be shared equally between you and the nitrogen. As a result of that, everybody has satisfied their octet. I have 1, 2, 3, 4, 5, 6, 7, 8 for that nitrogen. Oxygen is still happy even though he stole his lone pair and said, okay, nitrogen, let's share, because he's got 1, 2, 3, 4 in his dots, 5, 6, 7, 8. And of course, chlorine is happy with his 6 dots and his 1 pair of shared electrons in that bond line. So cool. If I'm 2 electrons short, we're just going to make a double bond. That sounds fun for me. What if I'm 4 electrons short on that central atom? And that central atom is like, yo, I need 4 more electrons from somewhere. Well, if the outer atoms are different, there will be one outer atom who is less electronegative than the other one. And if that's the case, this nitrogen is less electronegative than the hydrogen, he's actually going to take 2 pairs of electrons from him to form bonds between it and the central atom, and thereby I'd be creating a triple bond. So looking at that, now my carbon is satisfied because he's got 4 bond lines connecting to him, or 8 valence electrons. And my nitrogen, y'all, he's still satisfied. He's just got 2 dots and then 3 shared pairs of electrons, so he's cool with 8. So that's what happens if I'm 4 electrons short and there's one outer atom who is less electronegative than the other one. I make a triple bond. But what if in this case, like carbon dioxide, both of those outer atoms are like totally the same, so there's not one that is less electronegative than the other? Well, in that case, I'm just going to take a pair of electrons from each one and form 2 more bonds between each atom and the central atom. So I will be making 2 double bonds. In both of these cases, though, that central atom is going to be able to get 2 more bonds, either a triple bond from one guy or 2 double bonds for both of his atoms. You get it. Okay. We will not be dealing with this because I'm not going to require you guys to really understand or assemble structures for the exceptions to the octet rule who have more than 8. But there may be a case where you have filled up your outer atoms, you have gone to your central atom and be like, yep, you good, you peace out, but your ticker is still not down to 0. So in this case, if there's still too many electrons left over, you're just going to place electrons like in pairs on the central atom until you're done. And you're like, that seems weird. This would just indicate that this molecular structure does have an expanded octet. Right. Now, we can also draw Lewis dot structures for polyatomic ions. You're like, what are you doing here? Polyatomic ions for ionic bonding. Yes, but do you remember last unit when I was like, oh, this entire NH4 plus ion, he's just collectively acting like a positive metal cat ion. And you cannot break him up when we write formulas. Do not touch that stuff. Well, the reason why I can't break him up, guys, is all of the guys, I keep saying that, all of the atoms in our polyatomic ions were all nonmetals. So they were all actually connected by covalent bonds together, okay? So I can now draw Lewis dot structures. I can draw a covalent Lewis dot structure for my polyatomic ions. But the key thing here is that now I've got to accommodate for a plus charge. I think in one of the earlier rules, it says all you have to do with that plus charge is that would just mean that atom lost an electron. So for your original counting of total valence electrons available, you would just remove 1 electron from that. But yeah, I could draw a Lewis dot structure. The rules are exactly the same after that. But the final thing that I've got to do is I got to put brackets around my structure and then show the charge on the upper right side. Okay, cool. That's it. And after that, I got step number 6. I just got to do a real quick final count to make sure I have not missed anything. Making sure all of my outer atoms have got a full shell. Making sure my central atom has a full shell. And you guys, this method works every time. I have been taught how to draw Lewis dot structures in many different ways. And I found in some way or another them to be kind of confusing or me to be feeling like unsure or not confident on when I was trying to draw structures. But this actually works like 100% of the time, which is I'm super excited about. Here are some practice examples. We're going to also do some practice examples here together on my next video that I'm going to record. But if you would like to pause the video right here, right now, and maybe on a separate sheet of paper, see if you can attempt to draw these structures based on the rules that we just talked about. So you can pause that right now. And then we can check our answers. The thing that I've written here in blue was my total count of all of the valence electrons from all of the atoms that are contributing in the molecule. And that represents the total number of valence electrons that I'm allowed to use to make bond lines and dots around all of the atoms in the molecule. A lot of these examples will be working out together on our practice packet. So if you have questions on some of these, maybe hold off your questions and kind of wait till we maybe answer some of those questions together as we work through things. Okay, here's some more. These are polyatomic ions. Keep in mind, I just said, hey, a polyatomic ion, if he's got a negative, just add an extra electron to that total. If he's got a positive, lose an extra electron from that total. So you can pause the video, see if you can work these out. And then we can check our answers, right? Noticing that both of these polyatomic ion structures, I put brackets around them and then the charge on the outside. Also noticing that here with my original count, if I were to count up 1 chlorine and 4 oxygen, I would have gotten this. And I added an electron to that because that's what that -1 charge tells me to do. So this would be my new starting total valence electron amount. Okay, same thing with this. If I just counted up 1 nitrogen and 4 hydrogen's valence electrons, I would have gotten 9. But here I have lost an electron. So I've literally removed from that 9 1 electron to where my starting before I draw my structure is going to be 8 valence electrons. Very cool, very fun. I actually do kind of want to talk a little bit more about these polyatomic ions now that I have revealed just, oh my gosh, wow, it's a covalent molecule inside there, just for the charge. So the atoms inside the polyatomic ion, they're all nonmetals and are all connected by covalent bonds here. So this would be the Lewis dot structure of phosphate. He's PO4 with a -3 charge. Look at that, you guys. How fun is that? So if I were to say, okay, well, an ionic compound, sodium phosphate, what would that look like for me? Well, remember when we drew our ionic bonds, we had these cations that were separated by their anions. Now, usually when we did our ionic bonds last unit, I did not give you a polyatomic ion because we did not know how to draw these covalent Lewis dot structures. I would give you a non-metal from the periodic table and you would put his symbol in brackets with the dots around and his charge on the outside. But here, I can do that with my polyatomic ion now too, which is actually really kind of cool and satisfying. So that would be the ionic dot structure for sodium phosphate. Okay. The final thing we're going to talk about, and we are going to do some of these examples in our practice packet, is I want to look at this specific polyatomic ion. This is nitrate. Now we know that I can draw a Lewis dot structure for him. I can put brackets around him. I can put his negative charge. I'm like, peace out, ready to go. Now, I get to draw in my structure, and I will have gotten to a point to where nitrogen would have to steal a pair from somebody else to complete his octet, making a double bond. But in this case, y'all, all of the outer atoms are different. I know I said that the central atom steals from the least electronegative atom, whoever that is. These are all oxygens. So I have kind of potential 3 different oxygens I can steal from. Which one is right? Really, none of them. The correct Lewis dot structure for a molecule like this, a polyatomic ion nitrate, is kind of more of a hybrid of all 3 of these things. And to make things even more complicated, which you do not know, but I think is very exciting, is research shows that there are actually no double bonds or single bonds in a structure like this. But it's kind of a collective average on where this double bond may, in fact, flip in between one of these 3 structures at a time. So we would call this molecular resonance. You were like, what is she doing here? This just brings us to our topic of resonance structures. So when you reach a point where you're trying to decide, oh my gosh, I need to make a double bond, but they all the same, I have run into a situation where I will have some resonance structures. So when more than one Lewis dot structure can be drawn, the molecule or the ion is said to have this resonance, where it looks like the double bond is flipping in between all of the outside atoms. So each one of these different Lewis dot structures are contributing resonance structures. So the key thing is when we do our Lewis dot structure practice, if you run into a situation like this, just draw all of the possible types of Lewis dot structures for all the possible resonance structures with little double arrows showing that resonates in between every single one of those bond types. So that is our quick little lesson on drawing Lewis dot structures, which oh my gosh, I'm so excited to practice with you guys and apply our rules and be like, oh my gosh, this feels so good and satisfying. I've never felt more confident in chemistry class before, but it's going to be super fun. So once again, I can draw these Lewis dot structures for covalent compounds because covalent compounds actually share their valence electrons to where I can make these lines that show that shared pair of electrons between the 2 atoms.